write on the whiteboard, where to find the recording, because obviously it does not make any sense to put the URL onto the recording itself if somebody does not have the URL yet, right? Okay, so the link to all the recordings that I have for all of my classes is youtube.com/someprofs, okay? And once you get there, they're all arranged by date, so that each recording has a name that is based on the date of the recording, as well as what class it is for. So if you're looking for cisp300, then you look for all the ones that has cisp300, and then you can go through a calendar and find out all the Tuesdays and Thursdays of this semester. That is how we can find out all the lectures for this class. Okay, so with that out of the way, I am going to take a look at the exam. So let me go find the correct folder first. You cannot see anything here because it's outside of the window for recording. And we'll pick one of the variations. I can use Zerno, so this way I can actually mark it up. 1199x1. We'll choose this one. There we go. All right. And there we go. Okay, here's question number 1. So, after I talked about the practice exam, I just found a new way to ask, about the same concept. So this one is, I give you the trace. And, in class, we go from the algorithm to the trace. So in this case, we're trying to look at the trace and ask, okay, what kind of pseudocode can give us this particular trace? Okay, so the first thing is, where do we start? Well, since we have pre all the way over here, so that means the first line of code of this particular pseudocode is on line 35. Okay, so we write 35 down, okay, as a line number. Okay, I'm going to use my tablet here because I can just write on top of here. So you can either use the blank area next to it or the area that's below it. It doesn't really matter as long as I can associate your answer with a question. I can grade it. Okay, so we start with line 35. All right, so we know there's a line 35. And according to the trace, what other lines do we know for sure we're going to have? Line 36, line 37, right? Okay, so 35, 36, 37. So we know we have at least these 3 lines. Now, whether we have some other lines or not, maybe we can determine that later. Okay. So when you look at the trace of line 35, what does it do? Does it have any comments? No. So if it has no comments, we know it is not the beginning of a conditional statement, like an if, nor is it the beginning of a while, because with all of those, we have to evaluate the condition, and then we have to say, is that condition true or not? Okay, it's missing entirely. What does it do instead? It updates variable a to 89. Okay, so how do we update a variable? What kind of statement updates a variable? An assignment statement, which we know as a left arrow in this class. Okay, so we say a gets. Now, your variable name may not be the same. Your first line number may not be the same. I randomize a lot of the factors, a lot of things in the test. So, but in this case, what do we put on the right-hand side of the assignment operator? 89. Okay, so there's that. Cool. Oh, I almost copied the wrong number. Okay, what about line 36? Now we are on line 36. And it says a does not equal to 90 is true. Okay, that by itself does not lock down what line 36 can be. But there are only 2 alternatives, are they? Right? So what are the 2 possible alternatives of line 36? What kind of statement, okay, begins with a question like, is blah, blah, blah true or not? A while is one, and then the other one is an if. Okay, very good. So there are two possibilities. So when there are two possibilities, then you have to think about, I don't really quite know which one, okay? So in that case, I'll just write down both, okay? So I'll say, maybe it is if blah, 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 then, but it can also be while something blah, blah, blah do, okay? But in both cases, what do you think is the condition? Based on the trace, does it tell you what the condition might be? What is the condition between the if then or between the while do? A does not equal to 90. Okay, that is really just copying from the trace into the algorithm that you are trying to construct. Okay, all right. So we say, okay, maybe it's a if then, maybe it is a while do, but either way, the condition is A does not equal to 90. Does that make sense? Okay, so by looking at only line 35 and line 36, I cannot differentiate between the two. Now we look at line 37. Line 37 does not have any comments, which means it is not a while do, it is not a if then. Okay, what do you think it's doing? It's updating A again, right? It's updating A to 90. So here is where you can have a variety of answers. Okay, so give me one possible answer. Yes. A gets A plus 1. Okay, that's one. Okay, very good. So we get A gets A plus 1. But the other one they can also use is just A gets 90. Okay, it's that I will consider that as a 100% correct answer, because in the lack of any further execution of line 37, you really cannot differentiate. Is it really just A gets A plus 1, which is the usual thing that we do in the loop? We change the variable. Or is it A gets 90, which is kind of strange in the loop? But that can happen too. I cannot differentiate between the two. So I would consider both as correct answers. Not a problem. Okay? But here's the important part. What do we do after line 36 executes? After line 37 executes? We go back to line 36. Does a if-then statement go back? No. So that means it cannot be the if-then, right? So we cross out the if-then, and then we say, oh, it can only be a while do. Is that okay? So if it is a while do, let's check whether it's doing what a while do is supposed to do, right? Because A is now updated to 90 because of line 37. When we get back to line 36, the question doesn't change. A does not equal to 90 is, well, this time it's false, right? So when it is false, we get out to post, which means there's no code after the while loop. So in order to be syntactically correct, or in order for this whole thing to end properly, there's an end while on line 38. And that's the answer. That's the whole thing. Now, if you miss line 38, and forget to indicate the end while, you'll get some deduction, but not a whole lot. Yep.
Let's say like you did it all like the same way, right?
Uh-huh.
For like line 36, you did the while.
On line 36,
Yeah.
oh, the while without the do?
Yeah. So I you didn't put while or do. I just put okay. So on mine, I put the A doesn't equal 90 because I
You get partial credit for that.
partial credit.
You get partial credit because part of what I want to test is whether you can tell whether it's a conditional statement or a loop. Yes? Say that one more time. Do? Or what if you are missing the do? There would be no deduction. As long as you mentioned while, or even as long as, okay? If you just use the English version of all of these stuff and go like, as long as A does not equal to 90, fine, not a problem. Yep. Line 37 is indented, but if you do not indent, I won't take any points off either. Because the question is really asking you, can you look at the trace and figure out what control structure can cause that to happen? Okay, and it did not say that you have to use the right indentation and all kinds of stuff like that. And it really is not the main point, so I'm not going to take any points off if there's no indentation. Do we have any questions about number 1? Okay, no questions about number 1. Then we are going to move on to question number 2.
I have a question.
Yes, go ahead.
When do we use
The else? Well, you only have an else if you have a conditional statement. In other words, the else can only appear if there's an if. It can only appear between the if and the end if. Sorry?
Why we do not use the else?
Why cannot we? Because this is not even a conditional statement. If it's a loop has no else. Only a conditional statement has an else. So in order to understand why we cannot have an else, you have to look at the picture, the trail map between a while loop and the trail map of a conditional statement. The word else is so that we can differentiate between, if the condition is true, we go to this side, or from your perspective, we go to this side. No, from your perspective, it's this side. Sorry, okay. So if it is true, we go on to the path that is on your left. If it is true, we go to the condition, or we go to the branch that is on your, no, the other way around. When it's false, we go to the branch that is on your right, okay? Yeah, because the mirror image thing is flipping me sideways. So that is when you use the else, is to say, if the condition is true, we do this, but if the condition is not true, we do that. With a loop, it doesn't have something to say when the condition is false. If the condition is false, we get out of the loop. There's no action to specify. Is that okay? So else does not apply to while. It only applies to if. Is that okay? All right? Okay. The next question, let me see, where's my pointer? Okay, here's the next question. So the next question is kind of based on what the practice exam has, but I changed it around a little bit, just so that, I can test you, not based on the practice test. So we have 3 conditions. I can scroll the screen up a little bit. Okay, so there we go. So the question is asking, when I'm done with the conditional statement from line 12 to line 24, I want the end result after that to be this. Z gets a value of Z equals to 0, but only if x is less than 7. I want Z to be 1, but only if x is greater than 70. I want Z to be 2, but only if x is greater than or equal to 7, but less than 43. I want Z to be 3, but only if x is greater than or equal to 43, but less than or equal to 70. Okay. So the question is, how do I construct C1, C2, and C3 to make this happen? Now, in your particular version of the question, you may not see the same constants, so these boundary constants will change depending on which version of the test you get. Okay, I think with some of the questions, I make 55 unique questions, so no 2 people in the class actually would have the same question. But I can grade it, not a problem. Sorry? Go ahead. Oh, okay. So this is usually what I do with exams. I just have variations of questions. Okay, so how do we make this happen? What do you think? So you have to look at the structure of the code. So if you look at the structure of the code and go well, I don't know how to look at this, okay? Then you have to remind yourself of what the trail map is going to look like, okay? So we have a conditional statement. We have 2 conditional statements inside a conditional statement. Have we seen something like that? We have a conditional statement where each branch of the conditional statement is by itself a conditional statement. Have we seen anything like that? The practice test has exactly that. Okay? So as far as the control structure is concerned, we have seen this already. Okay? So now we just draw the picture according to the structure of this code. So this is the outermost conditional statement. all conditional statements would look kind of like this. You have two branches, two things to do, but when you're done with one branch, then it's time to get out. This is the true branch, this is the false branch, and here we have C1. Is that okay? What if C1 is true? We have another conditional statement. What is that going to look like? A smaller version of this, right? That is inside that square or rectangle. So we have kind of something very similar that we put into here. Same shape, same construct, just smaller. Does it make sense? So the bigger the bigger construct is what is representing line 12, line 18, and line 24. This smaller one on the left-hand side is representing what is on line 13, 15, and line 17. What do you think is on the other side? What is inside the other rectangle? The same thing, right? It's also a conditional statement. So it looks exactly the same. But what is inside the box and the question that we have to ask would be different. Okay. All right, there we go. All right, so now the question is, what do we ask in C1 and what do we ask in C2 and C3? This is C2 and here is C3. Okay? So if this is the picture and the true branch is always the one to the left, what do you think I need to put in here? Do you see the little dot which is the cursor? So what do I put here? What is the statement or what is the line number corresponding to this smaller square, rectangle? X gets 0. X gets 0. Why? Because in order to end up here, what needs to happen first? C1 has to be true in order to follow this branch. When I get here, I have to answer the other question, which is C2. So is it going to be true or false? True again, to end up here. So in the pseudocode, that's exactly what line 14 is specifying is what if C1 and C2 are both true. Okay? So we put that here. Okay? We put Z gets 0 here. This becomes Z gets 1. This is now Z gets 2. And this is now Z gets 3. Is that okay? So are we understanding the structure of the code itself? So now we have to go back and say, but how do we make this happen? Because when I'm standing here, I will say, if I see Z being 0, that's a confirmation that X is less than 7. Okay, the only way you can set Z to 0 is through this rectangle, right? So that means the path that I have to trace backwards is going to be like this. So that also means whatever C1 is has to be true. Whatever C2 is, it also has to be true if X is less than 7. Is that okay? What about when Z equals to 1? Well, when Z equals to 1, it basically is confirming that X is greater than 70. So when you trace your way back, this time we're taking this side, which means C2 is going to be false, but C1 still has to be true. Is that okay? So how do we construct C1 so that both of these conditions will lead to C1 being true? And once we get to this branch, then we'll ask a second question, but we'll deal with that later. What do you think? Let me say that one more time. In order for C1, we have to choose a condition for C1 so that X is less than 7, X is greater than 70 will both make C1 true. How do we make that happen? And in the question, if you read carefully, it says here you can use logical operators like and or not, which is a huge clue to say that you might find one of these useful. So which one do you think is going to be useful in this case? Or, very good. Because if you say x is less than 7 or x is greater than 70 and use that as C1, it will steer you to the true branch when x is less than 7, but it will also steer you to the correct branch when x is greater than 70. Okay? So I'll just write it down here so that we can see C1 is x is less than 7 or x is greater than 70. Well, it depends on what you use instead. Then, with both conditions.
No, say like x is smaller than 7, then x greater than 70 is like you get the value of 0.
But that won't work. Okay, so you will get partial credit because you figure that x is less than 7 is somehow involved in C1. Okay, but you only get partial credit in that case because it is not addressing the entire thing. Okay, all right. So but are there any questions about how C1 works? Can everybody see that when x is less than 7, C1 is true? Is that correct? When x is greater than 70, C1 is also true. Is that okay? Now, just to be sure, we also want to make sure that when x is greater than or equal to 7 but less than 43, that C1 is false. Is that true? Okay, pick a number. Okay, pick a number between 7 and 43. Let's pick 20. When x is 20, is C1 false? Yes or no? Yes. Okay. When x is greater than or equal to 43 but less than or equal to 70, which let's pick 50. Okay. When x is 50, is C1 true or false? Also false. Okay. So we just kind of give it some random test cases so it can pass the sanity check. Yes.
I thought that either or was like if you have one true and another false, it would still be true.
That is correct.
Yeah.
Yes.
So how is that true or false?
When x is what?
If it's 20, how is that false?
When x is 20? Okay, when x is 20. Okay. Okay. Now, did anyone use either or in C1? Nobody. Okay. Because if you say either or, I would still consider that true because you cannot find an x to make both of these true at the same time. So either or actually is applicable in this case. Okay, so normally we don't want to use either or, but in this case either or would actually work as well. Okay, so do we have any questions about C1 itself, how it works? No questions? Okay, yep, go ahead.
Don't we have to state if it's possible or impossible?
Well, since it is possible, you have to give me the answer. Now, if you say that it is not possible, you have to give me an explanation. So I have to look at your explanation and see whether it makes sense or not. And based on that, you might get partial credit. Okay? Okay, so what this means is by the time we get to here, we know that x is less than 7 or x is greater than 70. Okay? But we only need one or the other side to be true for the or to be true. So that means at this point, I cannot differentiate, okay, is x less than 7 or is x greater than 70? We just know at least one of those two conditions is true. So how do we phrase C2 so that x is 0, but only if x is less than 7? We confirm again, okay? So C2 is x is less than 7. Because all we need to do at that time is to confirm that x is less than 7 in order to go to the branch leading to z gets 0. Because the false branch will automatically mean that x is greater than 70. Does that make sense? Because by the time we get to here, there are only two possibilities left. X is less than 7 or x is greater than 70. If it is not, if I'm not taking this branch, which means x is not less than 7, what is left that can be true? X is greater than 70. Okay? So if that is the case, then what about C3? By the time we get to this particular point, we know that x is less than 7 or x is greater than 70 is false. Okay? Huh?
X is like greater than 47.
We just have to confirm that x is less than 43. Now you can make it longer and more complex. I would not mark it as wrong, but you really only need to say that you only have to confirm that x is less than 43 as C3, and in order to end up with a value of 2. So I'm just going to give you the most minimal correct answer, and this one is just x is less than 43. Is that okay? Now this is, yeah, go ahead.
But to make it work, you would have to use the and statement if you were to make it longer, right?
That is correct. If you want to make it longer, the word but in English is the same thing as and logically. So if you say x is greater than or equal to 7, but less, and x is less than 43, that would be considered as 100% correct as well. It's just that x is greater than or equal to 7 does not need to be confirmed anymore because we did not take the other branch. Because if x is greater than or equal to 7 is false, then we would have taken the other branch already. So it is correct. It's just not necessary. Okay. So do we have any other questions about this one? This is the answer. No questions? Alrighty. And we move on to the two trace ones. Okay. All right, so this is the first trace question. So what I'm going to do is I will actually do the trace, but I'm cheating a little bit by using a program to do it instead of handwriting it, because handwriting it's going to take a little bit longer. So I'm going to cheat. But the test is not long enough, or the trace itself is not long enough that the tracing itself is going to cause, you won't run out of time just because you need to trace it. Okay. All right, so I'm going to overlay the spreadsheet right next to the code, so this way we can look at both at the same time. We need comments because we do have conditions to evaluate. We have line number as usual, and then we have one column per variable. So in this case, we have x, p, and also d. The variable name is also kind of randomized. So some people may get variable a, some people may get variable k, and so on. The line number or the start line number is also randomized. So some people may get 13, some people may get some other numbers. Doesn't really matter. The first one is pre, where we say question mark, question mark, question mark, because the question did not say assume variable blah has a particular value. So we put all question marks over there. For this particular question, I'm not going to take any points off if you forget about the pre line, okay, because that really is not what I'm testing. Yeah, go ahead.
Like the column of D with P is the problem?
You can exchange, the ordering of the columns is not important. So as long as I can see the updates of the variables are correct, you're still going to get full credit. Okay. All right. So on line 13, we initialize x to 3. On line 14, p gets a value of 16. And then on line 15, d gets a value of 0. So these 3 rows of trace will collectively give you some points, not a whole lot, okay? Because this shows that you understand what an assignment statement is and what to do. You have an assignment statement. So that will give you some partial credit, but probably not a whole lot. Okay? Then we get to the more fun part, which is on line 16. Line 16 is asking x does not equal to 0. Is it true or not? True. It is true, okay. And then we go to line 17. Line 17 says, we want to multiply d by 10 and then put it back into d. So since it's 0, 0 times 10 is still 0, so we put 0 back into d. On line 18, we have a conditional statement. X is greater than or equal to p. Is that true or false? Well, let's check, okay? P is 16 and x is 3. 3 is greater than or equal to 16 is false. Okay. And then where do we go? So this is one of the questions that some people ask me. So where do we go then? Well, normally we go between the else and the and if there is something to do, but we don't. Right? Yes. We go all the way to line 23. That is correct. So we go all the way to line 23. Now, if you write down something else over here and somehow just tell me that there's nothing to do in the else branch, but you don't know what line number to put down, that's okay too. Okay. In fact, if you say line 21, I'm not going to take any points off. Is that okay? The idea is we do not execute lines 19 or 20. Okay, we skip over those two. So on line 23, what do? We divide p by 2, so it becomes 8. And then where do we go? This is a while loop. It goes back to line 16. Okay, so line 16 is asking x does not equal to 0. It is still true. We go to line 17 again. 0 times 10 is still 0. We go to line 18. X is greater than or equal to p is false. Okay, but it's getting closer. So we skip to line 23 again. 8 divided by 2 is now 4. We go back to line 16. X does not equal to 0 is true. We go to line 17. D is still getting a 0. Then we go to line 18. X is greater than or equal to p is false because 3 is not greater than or equal to 4. And then we go to line 23. The 4 becomes a 2. Then we got back to line 16. X does not equal to 0 is still true. We go to line 17. 0 times 10 is still 0. And then we get to line 18. X is greater than or equal to p is now true. Right? So now what do? We get to line 19. We go to line 19. X is now decreased by the amount specified by p, so it is just 1. And then we go to line 20. We add 1 to d. D is now non-zero. Then we get to line 23. Okay, let me do this trick so we can still keep an eye on the header of the columns. There we go. So this way we can scroll the bottom part and still see which column we're on. So on line 23, we are dividing p by 2. P was 2 before, now it is down to 1. So when it gets down to 1, we have to go back to line 16. X does not equal to 0. It's still true because it is 1. We get to line 17. This time, 1 times 10 is 10. So we are now updating it. There's actually a different value. We get to line 17. Yep, this is 17. We now get to line 18. On line 18, we ask, is x greater than or equal to p? The answer is true, because 1 is greater than or equal to 1. Okay, so it is true. We get to line 19. X gets x minus p, so that means x is now getting down to 0. I just remember, when x is different from 0, we continue the loop. Should I exit the loop right now? No, we do not exit the loop until we get back onto line 16 to re-evaluate the condition. Okay, so this is 19. 20 is saying d get d plus 1. So here's d. So d is now 1, 1 or 11. We get out. We get to line 23. P is now p divided by 2. So you can write down either one. You can write down 0.5. You can write down 0. You can write down 1/2. It doesn't really matter, okay? Because the loop will exit anyway, okay? So if you want to write down 0.5, that's fine. If you want to write down 0, which is the floor of the division, that's fine too. Because at this point we get back to line 16, and guess what? X is not 0 is finally false, and then we get to post. And we are all done. Yep.
What if instead of 0.5, 1 over 5, 1 over 2?
1 over 2 is fine. Yep, yep. 1 divided by 2. Even if you say that, if you just kind of spell out 1/2, that is still correct. Is that okay? All right. Because the idea is I want to see whether you understand how a loop operates and how a conditional statement operates. Okay? So all of this stuff here is, me giving you a chance to demonstrate that you understand how the control structures operate. Yep.
So it's not about this question, but about question 1. If you use, like, how you use the x is not equal to 0.
Yeah.
Use that in question 1.
That's fine. Yeah. Yep. Not equal to you. In question number 1, you can say x does not equal to using the usual math symbol. You can use less than greater than. You can use exclamation point equal to, which is what C++ uses. Yep.
So before you did post rate, if I put like line 18 in there, so it's like false as well, I can like
You mean instead of post, you write down on. That would get you points deducted because we do not get out of the loop because of line 18.
No, I put 16 and 18.
You put line 16.
16 was false in the comments.
Okay, when 16 is false, you should get out of the loop right away. So you will still get points deducted because of that. Yep. Okay, so is that okay? Does everybody understand this trace? A little bit lengthy, okay? Yes? We're good? All right. So now we move on to question number 4 of 4. And I'll just open a new sheet to deal with this one. So the two pseudocode between question 3 and 4 have, I would say, have some similarities, okay? But they're not exactly the same. So we'll go ahead and get to the point where they are not exactly the same. So we got variable x again, we got variable p, we got variable q this time, and also variable d. So there are 4 variables in this case. And I might as well just make sure that we can see the header columns right now. Okay. And scroll the bottom one. Okay, there we go. So the precondition is still that we don't know anything about any one of these variables. But once again, if you do not write down the pre-line in this case, I'm not going to take any points off because it's not really the main point of this question. Okay. And then we'll start with line 15. So from line 15 to line 18 in this case, pretty easy stuff. Okay. We get 7 here. We get 100 over here. And then we get 9 over here. And then we get a 0 all the way over here, okay? And then we get to line 19. P is greater than or equal to 1 is, look at P has 100, right? 100 is greater than or equal to 1 is pretty clear. It is true, right? Okay? Then we get down to line 20. Now, line 20 is a different loop. It is a nested loop inside of the outer loop. So we still ask the question the same way. We still answer kind of the same way. So we say, is x greater than or equal to p? So x is 7, p is 100. 7 is greater than or equal to 100 is false. Okay. So now the question is, where do we go?
24.
We go to line 24. That is correct. We get past the end of the inner loop to continue execution. Okay, so we get to line 24, and line 24 just do some kind of basic arithmetics on p. P is divided by 10 and then store back into itself. And then on line 25 we divide q by 3. Remember we did a correction in class, so it is just 3 now. And then where do we go? We go back to line 19. Exactly. So the indentation of the while versus the end while is a visual way to tell where we need to go back to. Okay, because at the end of a while, you know that you have to go back to a while do. The question is, which one do we go back to? So the two cues that you can use is it's kind of like parentheses matching, open, open, close, and close. So you have to find the corresponding open parenthesis to this closed parenthesis. That's one way to look at it. The second way is to use the visual cue, which has to do with the indentation. Okay, so we get back to line 19. Line 19 is asking the same question. Is p greater than or equal to 1? It is true because p has a value of 10, which is still greater than or equal to 1. Oops, press the wrong key. Then we get to line 20. X is greater than or equal to p is, it is still false. Okay, so we skip that. We go to line 24. Okay, p is 10 divided by 10, which is 1. I think I glanced at one particular answer, and it was 10 divided by 10 was 0. Oh, that. Yep. Okay, so now we get to line 25. 3 divided by 3 is 1, right? Then we get back to line 19, and p is greater than or equal to 1 is still true. Okay, we go to line 20. And this time, x is greater than or equal to p is true. And then we'll take a look at this one and go like, okay, what do we do then? We go to line 21. X gets x minus p. P is 1. So we subtract, so it becomes 6. Then we get to line 22. D is d plus q. So it is 0 plus 1, which is 1. Then we get back to line 20. So we can see that there are just 7 iterations here. So we get back to line 20. It is x is greater than or equal to p. It is true. Line 21 goes from 6 to 5. On line 22, this one goes from 1 to 2. Go back to line 20. X is greater than or equal to p is true. So at this point, it's really just kind of boring and chore, right? So this is 4. This is now 3. Go back to line 20. Okay. This is now 3. This is now 4. Two. And then we get a 5. This is now 1. And this is now 6. And we have one last iteration to go. It is now 0. This one is now 7. And then we go back to line 20. X is greater than or equal to p is finally false. Okay. Then where do we go? 24. Line 24. Very good. And in this case, p is 1 divided by 10. You can state it either way. Okay. You can say 0.1. Okay, that works. Or you can say 1/10. Okay, that works too. And then you go to line 25. P is 1. 1 divided by 3 is 0.333. If you say 0.3, that's fine. If you say 1/3, that's fine. Okay, 1/3 is fine. Because it doesn't really matter. By the time we get back to line 19, p is greater than or equal to 1 is going to be false. Then we get to post. So we good with this one? All right. And that's the entire test. So what do you think? It was okay, easy. Question 2?
Yeah. Just the way it was written for me
Uh-huh.
made me more confused. Like when you went over it, I was like, oh yes, I understand exactly. But
Okay.
looking at it on my own, the way it was written,
Mm-hmm.
I was definitely confused.
So it was the decoding of the question that was kind of difficult.
Yeah.
Okay, all right. I'm just collecting feedback, so, if I can find a better way to explain what I'm asking for, I would do that. Anything else? Yep.
Probably, I personally prefer to have more homework
Okay.
and then have like all the things we do in the exam should not be a surprise or something for
Oh, that won't work. I intend to surprise you. I intend to surprise you. So the way my exams work, I don't really know about the other professors, but the way my exam works is if you understand the concepts, I can ask you to solve a puzzle that you have not seen before, but you should still be able to solve the puzzle because it is still testing you on the same knowledge. So there will still be surprises because that's kind of the whole idea of my test is to see if you can apply what you have learned, but not just to reproduce a process that we have done several times in class.
Yes, but 2 was a little bit hard.
2? Okay, so most people think 2 is a little bit difficult.
Yeah.
Okay, noted. Yes.
Personally, for me, like when we went over that same concept on
Uh-huh.
your quiz before, or your
The practice test?
before the practice test,
Uh-huh.
like that was definitely easier for me to understand where what the question was trying to ask, and like because I feel like you were trying to ask the same kind of things, right? I don't know, just
Okay. Well, if someone wants to rewrite the phrasing of that question, so that in the future I know, how I phrase that question, or what is a better way to phrase that question, please, feel free to email that to me, because I'm ESL, so sometimes the way I, explain something may not be the most straightforward way to do it. But I was told by my, Cantonese friends that I would do the same thing with my native tongue as well. So maybe it's not a language thing. It's a thinking process thing. So, are we good with the test? A review of that? Okay. All right. So we can move on to the current topic. Okay. Did anyone go back to the YouTube channel and kind of watch the very last part of the previous lecture? Good job. Thank you. Okay. Because we're continuing with that. Okay, so what I'll do is I'm just going to go to YouTube, so that, well, I mean, this serves 2 purposes. One is to show you guys, how to get back to the lecture content of a previous class. And the second one is, I really want that screen to be up so I can continue the discussion. So you just go to YouTube and go to some profs, and then you hit videos, okay? And then you scroll down until you find the date of the recording that we want. And it is going to be last Thursday, which is 7 days ago. And that's going to be the one on the 26th of September. Okay, so we click that. And all I need to do is to skip all the way to the end because I already know, what then it becomes I talked about on that day. I really just need, I know we only got 1 minute left. Few that's seconds all we need of this recording. What am I doing so to F? Can, for each iteration. Use that code here as the beginning point of today's increase lecture. By 1 for each iteration. So that means, so keep going a little bit. Okay. There we go. Okay, and we still have some seconds left. And pause. There we go. So can everybody read the code from last week, or is the font a little bit small for people in the back? Are we good? No? Yes? No? No? Okay, I can make this as big as I can. I think this will turn the entire screen. Yeah, that's not what I want. I think that's another one that makes it just a little bit bigger, but not. Oh, I don't know about that. Okay. I think we can do it like this, maybe. Okay, and then just move this tab up a little bit. Oh, come on. Is that better? Okay. So what we'll do is we are now focusing on find factor f of x, okay? We got the basic code, but this is not actual, not even pseudocode, because I have identified that we have some kind of a loop. And inside the loop, what we want to do is to increment f. And in order to get out of the loop, we want one of these 2 conditions to be met, okay? So let's go back and try to figure out what those 2 conditions are really saying. In other words, we're not just looking at the code. Okay, the battery just kind of crapped out. This is why we have rechargeable batteries. There we go. We're good to go again. So right now what we need to do is to go back to this code and figure out, okay, what does it mean when x mod f is 0? So do you still remember what is the mod operator? What does it do? Go ahead.
I forgot. It's not. You don't take the quotient, but the other one.
The remainder. Okay. So x mod f in this case is the remainder of x divided by f. Okay. We still carry on the division, but we toss away the quotient and we only keep the remainder. Okay. So we are checking the remainder of x divided by f. What does it mean when x divided by f, both being integers, has a remainder of 0? And how is it important in this context? Then we have confirmed, right? We just confirmed that f is a factor of x. Okay? All right. Well, is that a good reason to get out of this loop? What is the purpose of this loop? To find a factor, right? So once you have found a factor, I think we can get out of the loop. So we know why this is an exit condition. What about the other one? F times f is greater than x. So you can think of a prime number like 13, okay? And I will keep testing factors like 2, 3, and as stupid as it sounds, maybe even 4, okay? But once I have tested 4, this statement says 4 times 4 is 16. 16 is greater than x, which is 13. It's time to get out. 5 cannot be a factor. 6 cannot be a factor at this point. Does that make sense to you? Really? Okay. So let's think about another number. Okay. Let's think about 103. Okay, which is also a prime number. So with 103, how do you confirm it is a prime number? Okay, if you don't look up on Wikipedia or Google, okay, which is what most people do, is 103 prime, right? If you don't ask Alexa, and you don't ask your Google voice assistant, and you don't ask, what is the Apple product, Siri, how do you confirm that 103 is a prime number? Well, you really have to roll up your sleeve and try stuff out, right? Okay. So you say 103 divided by 2 has a remainder that is non-zero. Okay, we don't even care what it is. As long as it is non-zero, it is not a factor. Okay, 103 divided by 3 has a non-zero remainder. Divided by 4 has a non-zero remainder, and it keeps going like that, right? So eventually we'll try 10, and then we'll try 11. Okay, in other words, f will increment to 11 at some point. So we'll say 11 times 11 is greater than x, because 11 times 11 is 121, and x is 103 in this case. That tells me that we can get out. I don't have to test 13 or 17 or 23, none of those. Does that make sense to you? But why does it make sense to you?
Because the goal is to find the factor of 1 or 3. Once we get greater than 1 or 3, so we don't need to test it.
But why do we take the square of the potential factor and use that to test, to compare to the number that we are trying to find a prime factor out of? Why would that make sense? Okay, so we'll get back to this one. Okay, in other words, at this point in your mind, you should be thinking, yeah, it seems to work, but I'm not really 100% sure why it works or whether it works 100% all the time. Okay, so you should have this kind of knowing feeling in your head and go like, I am not sure. It seems to work, but I don't know how it works. Yes?
You already multiplied all of the lower numbers by themselves,
Yes.
and so if you were to try 11 times any of the lower numbers, that's redundant.
Okay, so what you're trying to state is, in order to have a product for x, one of the two numbers that you multiply in order to get x is going to be less than or equal to the square root of x. I think that is what you're saying. Yes? But can you confirm that? Can you prove that is the case? Okay? I think you have you know what it boils down to. So now the question is, can we prove it? Okay? But that's going to be a little sidetrack that we'll do a little bit later. So for now, we just say that, yes, we trust check that f times f is greater than x means that we can get out of the loop, okay? All right, so let's continue with this code, and we are going to use mouse pad because I can just type a lot faster this way. Okay, so I'm going to pull up mouse pad right next to here, so I can continue this code here. And I'll even say find factor f of x, loop f gets f plus 1, and loop exit when f times f is greater than x or x mod f equals to 0. Okay, so now we have to look at the next revision of this code, because I think we're missing a few things. Okay, first of all, what is the first value of f? Okay, so in other words, I'm asking you, so here's 103. What is the first prime factor that you should try? 2, okay? Not 1, because if you start with 1, then everything is divisible by 1 with no remainder. So we want to start with 2. So that means we have to initialize f to something, okay, outside of the loop. This cannot be done inside the loop. And then the second thing that we have to consider is, well, what kind of a loop should this be? We have 2 choices. Can someone remind me of the 2 choices that I have when I know that I need to use a loop, but there are 2 variations that I can choose from? What are the 2 variations? I can do a while loop, which is a pre-checking loop. We check the condition first, and then we do something. What about the other one? It's a post-checking loop, which is known as a repeat until. Not if, okay? If is not a loop. If is a conditional statement. It is not a loop, okay? A loop means by the time we get to the end of the construct, we go back to the beginning to do the whole thing all over again. A conditional statement, an if statement, does not do that, okay? So what do you think? Which one should we use? Well, I think, if we can use a while, we should always just go ahead and use a while. Okay, so I'm going to convert this to a while here. But the while condition is going to be exactly the opposite of the exit condition, because the condition that we have up to this point is what we call an exit condition, which tells me when I can get out of the loop. But the condition that I have to put next to the while is the condition in order for me to stay in the loop, which is exactly the opposite of the exit condition. Is that okay? So how do I turn f times f is greater than x or x mod f equals to 0, and how do I negate that logically? Yes?
F times f is less than f, or the amount of f is not 0?
Well, you got most of it. Got 2 minor little things that I'm going to nitpick on. Okay, so the first thing is, okay, f times f is less than x. Okay, it can be here, but it should be less than or equal to, because the opposite of greater than is less than or equal to. But I might have misheard. You might have said equal to, but I didn't hear. But the more important part is, if the or turns into an and. Okay, so we have to say and x mod f does not equal to 0 in this case. Okay, so that becomes the stay in loop condition. The question is, does that make sense? Okay, convince me this is the right way of doing it. F times f is less than or equal to x means I cannot yet confirm that x is prime. Okay, x mod f does not equal to 0 says f itself is not a factor of x. So basically, I'm saying I have not found a factor of x yet, and x is not confirmed to be prime itself. Then what do? Try the next available f, right? So the way we try the next available f is to say f gets f plus 1. So we go from 2 to 3, 3 to 4, and so on. Is that okay?
Are we supposed to initialize f?
Yes, we are. But I cannot say which way to initialize until I know what type of loop we are dealing with. So now that we know we're dealing with a pre-checking loop, what do you think f should be initialized to? 2. Yep, because 2 is the first prime number that we should try. Okay, we're almost done. when we are once we get out of the while loop, okay, there are two conditions that can get out of the while loop, right? One condition is f times f is greater than x. We get out of the loop when that is true. The second one is when x mod f does equal to 0. We also get out of the loop when that happens. Because remember, this is a conjunction, it's an AND, which means if at least one side is false, the whole thing becomes false. We have two reasons to get out of the loop. But depending on which reason we get out of the loop, we might need to adjust f. Okay? So let me ask you this question. If I can confirm that f times f is greater than x, what should I do? Now you have to remember what is the objective of this entire pseudocode. The objective of this entire pseudocode is to find a prime factor f of x. Okay? And here I have just confirmed that f times f is greater than x. Let's think about an example. Okay? X is 101, which is a prime number. F is 11. Okay? So the question is, what should I do in that case? Because if I don't do a single thing, then f, which is 11, is now considered as a factor of x, which it is not. So what should I do? I have just confirmed that x is a prime number, and f is representing the last potential factor that I have tried out. F gets no. What is the prime factor of x in this case? What is the prime factor of 101? It is itself, right? So what do I need to do to f? You got part of it right. We need to update f, but what should we update f to? To x, right? Yeah. Okay, very good. Because x is its own prime factor, so now we have to report back to whatever code is trying to make use of this pseudocode that, oh, by the way, you just gave me a prime number. It is its own prime factor. So you're correct partially, and you finished basically the solution. So good job. So are we good at this point? Yes? Okay. So I can spend some time to trace this, but instead of tracing this code, which you can do, okay, so I want you to kind of give this code line numbers and then trace it. And when you trace it, I would say you have a precondition of x being a composite number for a few examples, and then have x being a prime number for other few examples. So I would try, I would even write this out so that you guys know what test cases you should be using. So try out, x being, let's try a small, prime number. Let's say 11, okay? See what happens. Try out x, as a composite of two prime numbers, okay? Let's say 15. And try again when x is the square of a prime number like 25. So I want you guys to try out these three cases on your own, to produce a trace and see and make sure that you can see how the loop exits correctly and how we adjust so that f always becomes the prime factor of x. Okay, so that's kind of your ungraded assignment, because that will give you some practice of how to go through the loops. Yep.
So the conditional statement, would it be after the while loop?
Yes, the conditional statement is after the while loop, because until the while loop exits, we don't really have any reliable f to make use of. So after the loop, we get to the conditional statement, because if f times f is still less than or equal to x, how do we get out of the loop, right? Because if f times f is less than or equal to x, which means this condition is false, that means we must have gotten out of the loop because x mod f is not 0, it's false. Okay, wait, hold on a second here. X mod f does not equal to 0 is false is a very roundabout way of saying x mod f is 0. But that means f is a factor of x. But that means, oh, we really should not be doing this because f is a legitimate factor already. So don't overwrite it, right? So that's why it is after the loop. That's a good observation. Okay, so what I want to do for kind of the rest of this class in the next 10 minutes is to prove what you have observed earlier, that if a number, let's say c, is the product of a and b, then one of those two, A or B is going to be less than or equal to the square root of C. At least one, okay, because C can be a square. Is that okay? So that's what we're going to do. And to do that, I think I'm going to use Zerno to do that. And I'll just attach a new page to here. New page after. Okay, there we go. All right. So what we'll do is I'm going to say this. Okay, I will say, okay, this is the theorem that we want to prove. Okay, the theorem is, okay, first of all, A, B, C, they're all integers. Or let's make these counting numbers. Counting numbers. So counting numbers is just a fancy name to say non-negative integers. Okay, you can look at these as natural numbers too if you want to. So either way is fine. Okay, it can include 0, it can exclude 0. You know, either way works. Okay. If A times B equals to C, then A is less than or equal to the square root of C, or B is less than or equal to the square root of C. Okay, that is the theorem. Okay, does everybody understand the theorem itself? What is the point that I want to make? Okay, very good. So we're only dealing with integers here. We're not dealing with fractions. We're not dealing with irrational numbers, just positive integers. Okay. So the technique to prove this is called proof by contradiction. Don't worry, in this class I will not test you to see whether you know how to prove by contradiction. But if you're on the computer science transfer track, eventually you will have to take CISP 440, and then there will be proof assignments or questions in that class. Okay, so eventually we'll get to that. So proof by contradiction, proof by contradiction is interesting because what it says is if the theorem is wrong, we're in big trouble. That's basically what it's saying. Okay, so think about it one more time. Okay, I'll say that one more time. If the theorem is wrong, we're in big trouble, and as a result, the theorem has to be true. That's the premise of proof by contradiction. Now, don't quote me in front of a math professor because I was using very casual words, okay? But the idea is the same, okay? So I have to negate it first. So we have to negate the theorem. So we have to what we call negate the theorem. In other words, what does it mean when I say Tech just lied? The theorem is wrong. So what is the opposite of the theorem? If the theorem is wrong, that means I can find A, B, C as counting numbers, but even though A times B is equal C, both A and B are greater than the square root of C. Does that make sense? Okay. So let me write it down here. Okay. So the Negator theorem is A, B, C are counting numbers. We still maintain the definition of A, B, and C. So A times B equals to C. But we say that A is greater than or equal to C, and B is greater than or equal to the square root of C. Okay? Does that work for you? If this is what you pay for, let's say you pay $100 and I tell you this particular theorem, and today you're running out of cash and you want that refund for that $100, then you have to say that, hey, if tech is wrong, that means I should be able to find, three numbers, A, B, and C, so that C is the product of A and B, but A and B are both greater than or equal to the square root of C, right? That's how you get your That's how you get your $100 back. Does that make sense? Yep.
Why is it that it's greater than or equal to if it's negated? Wouldn't it just be greater than?
Oh, it's greater than. You're right. Okay. You're right. Okay, I goofed here. There we go. Thank you. Good job. Good job catching these little things. So this is the Negator theorem because A is less than or equal to C. Is negated is A is greater than C, greater than the square root of C, And the same thing for B. Okay. So first of all, if I say, if you can find me this particular combination, 3 integers or 3 non-negative integers, A, B, and C, such that C is the product of A and B, but both A and B are greater than the square root of C, and I say, if you can find me these 3 numbers, I'll give you an A in this class, no questions asked. The question is, will you spend the rest of this semester hunting for these 3 numbers? What do you think? And why not? You cannot find them. So now the question is, why can't it happen? Okay, that is the question. Why can't it happen? Okay, so let's see what happens when we have these premises. Okay, so we are focusing only on this part here. A, B, and C are integers. C is the product of A and B, and both A and B are greater than the square root of C. Okay, so what we'll do is we're going to say, okay, so we know that A times B equals to C, right? That's a given. All right, so let's see. That equals to the square root of C times the square root of C. Yes? Okay. But do you see a contradiction here? Because A is greater than or equal to the square root of C, right? So because A is greater than or equal to the square root of C, and B is also greater than or equal to the square root of C, if you combine these two, don't you think A times C should be greater than, oops, I keep using greater than or equal to, but it should be just greater than. Okay, there we go. Does that make sense to you? None of these numbers is negative, okay? Wait, but what is the square root of C times the square root of C? That is just C. So we have A times B being greater than C, but we are also given that they are factors of C to begin with. These two cannot be true at the same time. So when I can use logic to say that, yeah, A and B equals C as a given, but A times B is also greater than C because of the assumption that A is greater than the square root of C and B is greater than the square root of C, then we have a contradiction. This cannot happen. Well, if the negated theorem causes a contradiction, then what do we know about the original theorem before it was negated? It has to be true. Okay. So we got 1 minute left, which is what we need in order to bring this all back to the program, the code that we wrote today. Why is that important then? Why is this particular theorem important? What role does it play in the algorithm that we just wrote? We keep testing from 2 to 3 to 4 to 5 to 6, 7, 8, 9, 10. When we get to 11, and the number in question is 101, what can you say? There are no factors. 101 has no factor other than itself, because if it had any factors, we would have found it already, because one of those factors is guaranteed to be less than or equal to the square root of 101. So if it had one, we would have found it already by the time we get to 11. Yes?
It's like trial by error?
Yes. So the algorithm itself is trial and error. But most people would try to do it all the way up to like 51, okay, or 52. Then we say, no, we don't have to get to 52. Or some people would actually try all the way to 100 itself, just one below the number, okay, to confirm it's a prime number. Then some people say, no, you only have to get to 1/2. No, you only have to get to the square root of the number. So when x is a large number, this can save you a significant amount of time. Now, when x is small, it doesn't really save you much time. Okay, so when x is, say, 5, okay, how much time does it save you? Not hardly any, right? But when x is like a 9-digit number, then it can save you a tremendous amount of time. So that's the end of today's lecture. So this stuff here is more like an exposure to a mathematical proof of a concept that we utilize in programming, but it is nonetheless an important concept. I won't test you on proofs. I'll see you guys next Tuesday.